after that. So lecture number 10 might be my favorite lecture of the year because I get to tell you about my favorite algorithm, which is MiniMax. MiniMax search, and then on top of MiniMax, we get to do something called AlphaBeta pruning. And this is our first foray into this sort of multiplayer game universe where now instead of just solving mazes or computing paths, you're actually competing against another AI system. So this should be really interesting. Multiplayer games. So far in this course, we've only really looked at problems with a single agent. And so that's called single agent search. So for example, solving a puzzle or trying to compute a shortest path in an environment. Heuristic search can also be applied to environments or games with multiple agents, or in the case of games, it would be multiple players. And as we talked about before, games can have a number of properties. Multiplayer games can have a number of properties that are similar to single agent environments. So for example, games can be fully versus partially observable. They can be deterministic versus stochastic. They can be dynamic versus static. And they can also have different number of players. So for example, how many players are in the game? You might have to decide, well, okay, I'm making a game or I'm trying to apply an AI to the game. Well, the type of algorithm that I can apply, so for example, some algorithms can be applied to deterministic games, but not stochastic games. And just like that, some algorithms can be applied to games with one player, like a puzzle or a Sudoku or something, but not games with multiple players. So examples of the number of players in games, if we're talking about chess or Go or traditional board games, usually there are 2 players. In baseball, we may be talking about, well, there are 18 players, but maybe there's only 10 players at a time and there's 2 teams, so we can think about different games and different players in different ways. In StarCraft, for example, we might be playing 1 versus 1, 2 versus 2, or actually like a free-for-all where everyone is just trying to survive. In something like poker, we could have 10 different people at the table all trying to win each other's money. So games can have different amounts of players just like they can have other properties as well. What about the payoffs for a game? So we just got done with our sort of introduction to game theory and we talked about payoffs. What does each player hope to achieve in these games? This is also very important, and it also defines what the algorithm is that we're going to be using. So for example, in the prisoner's dilemma, we wanted to maximize our utility or maximize our reward or payoff from that game. In poker, we may just want to maximize our own profits. So we don't care about what happens to anyone else. There's a bunch of people playing. We just want to win money. In chess, it might be a little bit easier. It's just win the game, right? I'm playing against someone else. There's a winner and a loser, so I want to win. There's a concept of a zero-sum game in game theory. And I didn't go into this much because it's not super relevant to the course. But in a zero-sum game, each player's gain or loss is equally balanced by the gain or loss of another player. So in a zero-sum game, so for example, if we're playing 1 versus 1 heads-up poker, if there's no rake from the casino and all that, basically, if in order for me to win money, you have to lose money, right? In order for me to win a game of chess, my opponent has to lose the game of chess. And so this is the concept of a zero-sum game. And in the case of a game where there is a winner and a loser, now there might be draws as well, those are zero-sum games, okay? Typically we would say a win is a 1, a loss is a -1, and a draw would be a 0. And the cool thing about zero-sum games is that zero-sum games, there is guaranteed to be a Nash equilibrium. That's pretty cool. So most traditional board games that, like chess, Go, checkers, all that kind of stuff, usually they are 2-player, zero-sum, alternating move, perfect information, deterministic, and discrete. For the most part, right? You can look at some of these and you can easily come up with games that don't fit this. Like, for example, card games are not perfect information. There's hidden information that you don't know about the opponent's cards or something like that. If you think about something like backgammon or Monopoly, there might be dice, right? And so that makes it stochastic and not deterministic. So we're going to be dealing with algorithms that solve these type of games, okay? The traditional board games with no randomness, no hidden information. And who out there can tell me the name of this computer? This is probably the most famous computer of all time. It's called Deep Blue. And Deep Blue was invented by IBM and a bunch of researchers at IBM and other researchers at various academic institutions. And it was the first computer to beat a world champion at chess. And so that was a really big moment in sort of the history of AI. It was by far the biggest headline that artificial intelligence had ever made in the world up to that point, was that a computer had finally beaten the world champion at chess. And that was Garry Kasparov, I believe in 1997. So how could we design something like Deep Blue? Excuse me. How could we design an algorithm to play a two-player alternating move game? Well, there's a bunch of different things that we could think about. And maybe we'll go in like different levels of complexity. So let's just think about different ways that we could possibly implement an AI for a game like this. So the first one, we might say something like, okay, as a chess player or as a checkers player, as a Go player, maybe I've done some analysis of the game. I've read a bunch of books. Excuse me. I know some basic strategy. I know some tactics. And what I'm going to do is I'm going to try and turn my knowledge of the game into like a program that plays the game. So for example, maybe I want to take pieces that are near the center of the board. Or I'm going to like add up the value of the pieces on the board, and if I have more pieces, then I'm winning the game or something like that. So some basic analysis. It turns out that this is what players tried to do at the very beginning, like back in the 50s, 60s, 70s, before there was a lot of computation. And while it did produce a system that could play the game, this couldn't get anywhere near the strength of the best players in the game. So what about thousands of if-then statements, right? This is the next possibility. We've identified a number of key positions that you could be in when you're playing this sort of game. And you say, okay, if you're in this situation, do this move. If you're in this situation, do this other move. If you're in this other situation, do this other move. And what happens is, as we'll see, there are far too many situations in interesting games to allow that to be possible. Now, that doesn't mean that you can't make an AI that has a bunch of if statements in it. Like, for example, a lot of very early video game AI was just if-then statements. If Mario is over here, walk toward Mario. That is a very fine AI for that purpose. But if we're talking about, sort of hardcore, be the best possible solution for AI, then usually if-then statements do not cut it. Let's try a new idea called, I'm going to call this, let's try some stuff, right? So we'll try some actions, and then we'll evaluate those actions. So what we'll do is we'll say, okay, here's the different things that I'm capable of doing right now in this game. How about I try those things and see where I end up? Okay? So this is what this looks like. If I'm at a current state of the game, I'm going to generate a list of actions from that given state of the game. Then I'm going to evaluate those actions based on the features of the resulting state. And then I'm going to do the action which has the highest evaluation. So let's say I'm at this current state, and I'm going to say, okay, I'm going to try action 1, I'm going to try action 2, I'm going to try action 3. I'm going to move my queen to here, I'm going to move my pawn to here, I'm going to move my bishop to here. And then I'm going to look at what would have happened if I had done that stuff, and then say, which of those do I think was the best? Okay, so here's a function that we could use to implement that. So here's my look ahead and evaluate function. So here's my look ahead and evaluate. I pass this in a state, right? So I'm going to be taking the maximum of something. So in order to do that, I'm going to record my current maximum value. And you typically do that by setting that equal to like minus infinity, right? And so I'm going to be taking the best thing, the highest valued thing that I find. Then I'm going to record the best action that I found at some point. So here's the main loop. I'm going to look at my state, and I'm going to get all the legal actions that I can do from that state. So for each action in the legal actions, I'm going to create a new state, which is the child state. And I'm going to say, hey, state, do the action that I'm currently looking at, and create a new state called child. Then I'm going to have some function which evaluates that child state and come up with a value, right? So this might be 10, it might be 1,000,000, might be whatever. If that value is a new best value, then I'm going to record that new best value and mark this action as the best action that I've seen so far. And then what's going to happen is we're going to evaluate the next action and the next action and the next action. And then I'm going to return the best action. So here's an illustrated example of that. Let's say we're playing tic-tac-toe. Now I'm right here in this stage of the game and it's my turn to place an X. Okay? So I'm going to try all of my available actions. And my available actions are, I can put an X here, up on top. I can put an X in the middle. I can put an X to the right. So I'm going to try all those actions and create some child states. So if I put the X in the middle, I get this state right here. Now I'm going to evaluate that state. And I'm going to say, oh wow, I've actually won the game at that state. So that is going to get my maximum possible evaluation. Either 1, if I'm scaling from 0 to 1, it's going to be a 1. If it's scaled from 0 to infinity, I'm going to get infinity. The best thing I can do in tic-tac-toe is win the game, right? So that's a really good evaluation. Now, if I look at this state, well, I haven't won the game, but I also haven't lost the game. So maybe this gets like a 0, right? Because I haven't fully evaluated everything, but nothing bad or good has happened yet. Similarly, if I put my X over here, well, it's the same kind of situation as right here. I haven't won, I haven't lost. So there you go. Now, so what I would do is I would return this action right here. But as you can see, this is a flawed way of doing things. I'm only looking one move ahead, right? And as I'm sure you're saying out there, this is a really, really bad move because my opponent is going to be guaranteed to be able to win by placing a 0 or an O in the middle on the next one. But this example that we just did, all it does, that function, is look one move ahead. Okay? So you can see now that we're probably going to want to do something a little bit more complex than this. So how about we search the entire game tree? So for example, could I look at everything that I could do, then everything the opponent could do, then everything I could do, and sort of this like me, you, me, you, me, you? Could I do something like that? Well, let's have a look. And we've already kind of answered this question in the game. And it turns out that the game tree is just really big. So we have some number of actions possible at each state. That's called the branching factor. And the game is going to end after some number of moves. And so the size of the game tree is b, the branching factor, to the power of the depth, right? And so state and action spaces, so the state space and the action space, which we already talked about, the state space is the number of possible configurations of an environment there are. The action space is the number of actions that are possible from a state. And so we estimate the complexity of the game through these values. And so the way we compute these things is essentially by taking, and we've done this already, so I'm not going to go in depth with the calculation, but it's by taking, if we have a board like chess or checkers or whatever, we take the number of possible pieces that could be at each state, and we take that to the power of the number of board states that there are. And so we can see that for tic-tac-toe, there might be 10,000, right? For chess, there ends up being a lot more than 10,000. This number is very, very big. I'll just let the animation play out. And so what we end up with in the end is 10 to the 42 or 10 to the 43 possible chess positions. And when we have a game like Go, it ends up being even bigger. So I won't play the whole animation out. But what we see here is we asked the question, could we just search all of the moves for the entire game, right? So if we want to answer that question, we should figure out how many moves there are. So for tic-tac-toe, this is just the number of possible states that there are in a game. And as I said, as we talked about before when we did this analysis the first time, there are actually far more game tree, the space of the game tree is higher than the state space. So the state space, again, this is a good exam question. The state space is the number of board configurations. The game tree space is the number of possible games that could be played, right? So the number of different sequences of moves that there are possible. So for example, of the 10 to the 43 possible chess states, there are way more game trees because there are millions, if not billions or trillions of possible ways to get to every possible chess state, right? So this value here measures if we wanted to search the entire game tree, how many operations would we have to do? And 100,000 or 10,000 for tic-tac-toe, that's fine. For tic-tac-toe, we could feasibly, in like a millisecond, search all of the possible states of tic-tac-toe. But as soon as we get into bigger games, we cannot even think of searching the entire game tree. So we said, okay, let's try to look ahead one depth, right? That didn't work because we want to analyze more things, but we can't search the entire game tree. So I think the natural place to fall is somewhere in the middle, which is let's look ahead as far as we can. And what does as far as we can mean? Well, it means whatever our resources are capable of doing. So we may say, okay, maybe I can search a total of like depth 2 or 100,000 nodes, or I'll search for an hour, or whatever our time or memory constraint is. That's how far I will look ahead. And hopefully this will give us enough information to make a decent decision. Now, when you have competing players, so before when we looked at the search tree for a single agent search, every node was connected by edges, right? So we have nodes that are connected by edges. When it was a single agent problem, every edge was the action that, for example, with pathfinding, took you from the state of this node to the state of another node. Every action in a single agent search belongs to the same agent, right? It belongs to the only player of the game. When we're talking about now having two players in a game, and those players are competing, and again, this only applies to alternating move games, we have one player doing one set of actions, and another player doing another set of actions. And so at some particular depth, the nodes will specify, okay, all of these nodes, these are player one's moves, and these nodes, this is where player two can move. Okay, so if we have a node with a node here in the game tree with a corresponding color, I'm just color coding these. This might be player one, and this might be player two. At some point, we're going to reach the limit of our search, right? Either we've run out of time, or we've set a depth limit, or we've run out of memory, or something like that is going to happen where we have to say, okay, we haven't searched the entire game tree because that's too big, but I have to stop here. I just have to stop. Something is telling me to stop. And what I'm going to do at that point is the leaf nodes of this search, I am going to apply an evaluation function to that search. And that evaluation function, or to those states. And that evaluation function typically is going to say something like, I want to be in that state this much. It's this good for me to end up in that state. So ideally, what I want to be able to do is take the actions that will lead me to that state. But what you have is, you can't just go straight to the state that you want to do, because there's another player trying to do the opposite of that. So let's have a look. If you have player one, so let's say that the root node of this game tree, I'm currently playing chess, for example, and I have the white pieces, right? So I'm going to go first. So player one. Then player two has the black pieces. They're going to go after me. What I'm going to say is, okay, after I've moved and then after the other player has moved, maybe my limit was a depth 2 search for whatever reason. So after player 2, the other player has made their moves, I'm going to end up with some evaluation. I'd love to end up here because an 8 to me is the best of all of these states, right? So over here I have a 2, that was like kind of a bad state. I don't really want to be there. Oh, a 6, that's pretty good. I'd like to be there. A 1 is here, that's really bad. An 8 is here, that's really good. So ideally, I'd like to end up in these states. But there's another player who's able to take actions, right? And I'm trying to maximize my outcome, but they are trying to minimize my outcome. All right? So when we take a tree to look like this, instead of saying player 1 and player 2, it makes sense to frame it like this. The player who's trying to maximize the values and the player who's trying to minimize the values. Okay? So, again, think of a game of chess. I've got a number of possible moves that I can do, and the opponent is going to have a number of possible moves that they can do after that move. We've looked at all of those possible scenarios. So if I have these 2 actions, and then after those 2 actions, my opponent has 2 actions. Now for a game of chess, it would probably be like 50 actions or something. But we've gotten to this level where we have applied some evaluation function. And we've said, okay, I prefer to be in either this state or this state. But before these states, it was actually the opponent's choice of move. And the opponent is going to look at these evaluations and say, I want to minimize those values. So if the minimizing player is currently deciding, and it says, oh, look, I could either go to this state where there's a 2 or this state where there's a 6, well, that's my opponent, and they're going to choose to go to the 2 state, right? Because they want to minimize the best thing that I could possibly do. If instead my opponent was over at this node, they would look ahead and say, oh, this state leads to a 1 evaluation, this state leads to an 8 evaluation. So my rational opponent would choose the action that leads to the 1, right? So now, because the opponent was minimizing, and they could have either gone to this state or this state, then I'm going to have to maximize over these values, right? So it's saying, okay, my opponent has put me in one of these situations where they tried to minimize my result, but now I have a choice of the 2 things that they could give me, and I'm going to try and maximize that result, right? So of the 2 and the 1, I'm going to choose to go here because it's the best worst case scenario, essentially, okay? So I hope you see how that works. The player whose current turn it is the maximizing player. They are trying to get to the best evaluation state. But between me and the other player, there's a minimizing player trying to minimize my outcome. So we are competing in that respect. They want the lowest possible outcome for me, and I want the highest possible outcome for me. All right. So that's how that works. So as we saw before, this is this look ahead and evaluate function. Okay? Let's try and put what we just did into an algorithm. So what we just did was we said, okay, I'm trying to maximize something, right? But I'm trying to maximize the result of a minimize from the opponent. So at some point, we're going to have a minimizing function and we're going to have a maximizing function. Okay? So here's what that will look like. Here is a single depth maximizing function. So we have a max value function which takes in a state. We have this value, I'm going to just call it v for value. It's going to be set to minus infinity because we're trying to find the maximum of something. So for each child in the children of S, that just means, you know, for each action we would create the new child. I'm just sort of taking a shortcut here. For each child in the children of S, we're going to record the evaluation of that child. And if that evaluation is greater than my current maximum, I'm going to record it. And then what I do is I'm going to return the best value that I could have gotten. Right? See how that works? So what I'm doing here is essentially down here, but the maximizing version of that. Find the maximum value of everything one depth ahead of me. However, that's just for a single depth. If I want to look at that in terms of the full tree, right? So that was just this layer. But as you can see, the maximizing player wants to maximize the values of the minimizing player. And if we were to, have more depth in this tree, the minimizing player would be in turn minimizing the result of a maximizing player, who would be maximizing the result of a minimizing player. So we go max, min, max, min. Oh, maybe now you can see where the name of this algorithm comes from, the MiniMax algorithm. So that's a bit of a spoiler, okay? So the full tree would look something like this. If we are at a terminal state, and again, the terminal state is wherever we had to stop. So a terminal state might be where we reached a depth limit, we reached a timeout, or maybe the game was actually over at that state. Maybe we had won. So there is going to be something that tells us that this is a terminal state, meaning we should stop the search at that time. So if it's a terminal state, that is where I do the evaluation. Otherwise, I'm going to be maximizing. So I'm going to I'm going to set up a negative infinity for each child. Instead of just evaluating here, I want to maximize the result of a minimize, right? And so I'm going to get the value of that eventually and then compare it to my maximum, and I'm going to return that. However, there's a MinValue algorithm here, which is just the exact opposite of this, right? So we've got max value and min value, and this is what would happen on the full tree. So min value over here is the exact same thing as max value, except instead it is trying to find the minimum of something, so this v gets set up to positive infinity, and we're checking to see if it's less than that instead of greater than that. So look at this. We'll look at it one more time. Max value says, if the state is terminal, return the evaluation. Otherwise, take the maximum of all the min value calls. And min value is saying, if the state is terminal, return the evaluation. Otherwise, take the maximum of the max value calls. So let's look over here. And it says, okay, we're currently the maximizing player, right? So if this is a terminal node, evaluate it. It's not a terminal node. So I take the min player algorithm. Now the min player algorithm gets applied here, and it says, is this a terminal node? It is now. So apply the evaluation function and take the minimum of all of those. And that's what happens here. Now the maximizing player looks at its next action and says, is this a terminal node? It's not. And so the min player's algorithm happens, and then it applies that same logic to these two and sees that they are terminal nodes, so it returns the evaluation. And then once we have values here, then the max player is now free to actually maximize those values. So that's what this algorithm is doing. There's a maximizing part and a minimizing part, and they alternate at different depths of the tree, and those alternating maxes and mins correspond to me, the maximizing player, taking my turn, and you, my opponent, the minimizing player, taking your turn. Now, this again is for the full tree, right? And so we cannot do the full tree. So what we typically do is we apply a depth limit. And that depth limit we're going to apply, there's no changes to the algorithm. What we're just saying here is that terminal, instead of the state just being terminal, now we could be at a maximum depth. So before I said that terminal S, okay, we could be at a maximum depth. Terminal S here just means that the game would be over there. Or are we at a maximum depth? Okay, so those are the two ways that we could stop this process from infinitely recursing. Either the state is terminal, meaning that it's the end of the game, or some depth limit, maybe we have a depth limit of 2 here, that depth limit has been reached. All right? So we just add a depth limit in here. And then the only other thing that we have to add instead of this if statement is that when we then call the min value function, we have to pass in depth plus 1, right? Because here, we're at depth 0, here we're at depth 1, here we're at depth 2, here we're at depth 3. So we just, whenever we call that function, we have to call the next depth so that we can actually record that function. Now, this is all well and good. We have a maximizing function and a minimizing function. However, we want to put that into one function because it would be nice if our algorithm was a single function. So we have a min function, a max function. It mins, it maxes, it mins, it maxes. How about this algorithm is called the MiniMax algorithm? So this is what we've done. If we look here, this lines 2 and 3 of these two functions are identical, right? It just says if we should stop, evaluate the state. Otherwise, if we're maximizing, try and get the max. If we're minimizing, try and get the min. So what we can do to create a single function is just take this part and put it in an if statement. And that's what we've done. So we've got one other parameter here now, because here in the max function, we knew we were maximizing. In the min function, we knew we were minimizing. So the extra parameter here called max is just a Boolean which says, is this iteration of this function, should this be a maximizing step or a minimizing step? So I've got those same two lines up here that just says, okay, if we should stop, return the evaluation. Otherwise, if we're maximizing, maximize the value. Otherwise, we're going to be minimizing, so minimize the value. And we see here, the only other difference is that if we are maximizing, the next call, this is a recursive function, it's calling itself. So the next recursive call to this function, if we are maximizing, should be minimizing. So if we're maximizing, we pass false into the next call, so that we'll go to this branch. And if we're minimizing, we pass true, so that we'll go to this branch. See how that works? So we've taken the max function and the min function and just squeezed them together into a single function that both maximizes if I have to maximize or minimizes if I have to minimize. And that's it. That is the MiniMax function. And I know it's pretty simple, but it's very, very powerful. Now, here's a very interesting form of the MiniMax function or the MiniMax algorithm. It's called the NegaMax algorithm. And it's the exact same algorithm as MiniMax. It will produce the exact same result as MiniMax. However, because algorithm creators are super nerds and us people who do algorithm analysis and writing algorithms, we want things to be just as compact as possible. So what some person figured out a long time ago was that the max of A and B is equivalent to the negative max of negative A and negative B. So you can use that fact to get rid of the if statement, essentially. So we have the same two lines up here, and here we only have a single check, and it's saying that we're going to take the maximum of the negative result of NegaMax. And that works out because the maximum of A and B is equal to the negative maximum of negative A and negative B. So please don't implement NegaMax on your assignment. I just wanted to show you this because if you look up MiniMax online, and I'm sure you will, you might get this version of the algorithm. And you might say, what the hell? Why doesn't it have this if statement? Well, here's the reason for that. But trust me when I tell you, this version of the algorithm, even though it's a little bit cleaner, it is way harder to understand conceptually, and it is way harder to debug practically, okay? Because you don't know when your error is occurring, if you're maximizing or if you're minimizing. It's a bit of a nightmare. So while it is, in theory, the exact same algorithm, in practice, I don't recommend implementing it. Let's look at the properties of the MiniMax algorithm now that we have shown the MiniMax algorithm. MiniMax is complete and it is optimal. It will find the optimal solution up to a given depth, right? So if you have said, hey, search the whole tree, if we have infinite computation time, it will find the best possible answer. And each player plays a best response to the possible actions of the other player. Look at this. Isn't this really cool? So the minimizing player is choosing the best thing for them. And then once it chooses all of its options, the maximizing player is choosing the best thing of all of these. So at each depth, it's a series of best responses. And from our last lecture, what happens if we play best responses? What is the definition of when everybody is playing a best response to everybody else? What did we call that? All right. Well, we called it the Nash equilibrium. So, if for two-player, okay, let me say one more thing. If we can search the entire tree, which typically we can't, MiniMax will play a Nash equilibrium. So it will play the strongest possible move if we can search the whole tree. If it doesn't search the whole tree, then what we say as algorithm people is that MiniMax approximates the Nash equilibrium to a given depth, okay? So it looks for all these best responses and does the best that it can, given that it can't search the entire tree. So we talked about Nash equilibrium last time. There's a really cool thing for two-player, finite, zero-sum games, a Nash equilibrium exists. And recall, each player is best responding to each other in a Nash equilibrium. Neither player can gain by deviating, and neither player has any regrets. So playing a Nash equilibrium is a very strong strategy. Cool. That's MiniMax. MiniMax will approximate the Nash equilibrium. We've already shown that playing the Nash equilibrium is something you probably want to do. Therefore, MiniMax is going to give you a very good move. However, can we improve MiniMax? Can we? MiniMax is already a great algorithm. Can we do better? And the answer is a resounding, oh yeah, we can do better. And it's really cool. Let's look at this example, okay? Here we had this example before. We have a maximizing player, we have a minimizing player, and then we hit the evaluation node. So the minimizing player is going to be looking at these nodes and trying to minimize them. The first thing it says is, oh, so this node, the first child, that's a 2. So what can I think about now as a rational algorithm? So I actually know for a fact that the result of this node, what can I say about it? Just take a second to think about it. Pause the video and think. All right, you're back from the pause, right? The cool thing that we can say already is because this person is trying to minimize all of these nodes, that the result of this is going to be at most 2. It's going to be less than or equal to 2 because we're trying to minimize and we've already seen a 2, right? So now let's say we see a 7 over here, whatever. So the value of this is 2. Now, what do I know about this one? Well, this player is trying to maximize the results of these. And we already know what this player has chosen. So we know now that this value is going to be greater or equal to 2. Okay. So we know that that's going to be greater than or equal to 2 because I already have a 2 to choose from and I'm maximizing. So if this value ends up being less than 2, I don't care about it. So this player then looks at this node. It's not a terminal node, so min takes over. And now min looks down here and says, oh, this is a 1. So what do I now know as the minimizing player? Well, I know that this is going to be less than or equal to 1. No matter what this is, if it's greater than 1, I'm not going to choose it because I'm the minimizing player. So just look at this now. This is a very important point that I want you to not progress with the lecture until you understand the point that I'm about to make. Since the maximizing player knows that its value is going to be at least 2, and this value is going to be at most 1, then no matter what this is, it's going to be less than 2, because this is going to be less than 1, And so I can just say, screw it. I don't need to evaluate any of these nodes, because no matter what we end up coming up with here, if it's a 1 million, we will never be able to get here as the maximizing player, because the minimizing player will choose this. Okay? So if they're going to choose this, then this ends up, this is going to be less than or equal to 1. So it's not going to be chosen over this one. So I can just say, hey, stop all computation after this node, for this particular node, right? So I don't need to look at anything else, because this could be like, if it's a -5, it doesn't matter, because this has to be bigger than 2 for it to matter for this computation. So I'm pruning part of the tree, okay? When you go out and you prune an actual tree, that's what you're doing. So I know here that this is going to be a 2, right? Without ever looking at the computation of this. There could be a million nodes down here and it doesn't matter. This is called AlphaBeta pruning. So, AlphaBeta pruning is not a different algorithm than MiniMax. Sometimes you'll see online someone says this is the AlphaBeta algorithm, right? It's a bit of a misnomer. If I'm being really pedantic, which computer scientists, that's what we're known for, is being pedantic, there's really not an AlphaBeta algorithm. It's technically MiniMax algorithm with AlphaBeta pruning. But you will see almost everywhere people call it the AlphaBeta algorithm, and that's fine. Okay? But just realize that it's really not its own algorithm. It's an optimization to the MiniMax algorithm. And the cool thing is, it maintains all of the properties of MiniMax, but it's actually better because it cuts off a bunch of branches of the search tree and can yield exponential savings. So it does the exact same. If we do this cut, if we do this in the proper way and make these sort of observations that, okay, this is less than or equal to 1, this has to be greater than or equal to 2, so I can stop. In practice, the really cool thing is it usually results in exponential savings. And I've read a result out there somewhere that if your tree has n nodes in it, and you apply MiniMax, you'll have to evaluate n nodes. But if you apply AlphaBeta pruning, on average, you'll have to evaluate approximately the square root of n nodes. So that's crazy. Like, going from n to square root of n in terms of efficiency is a huge speed up. And so this is why it's called AlphaBeta pruning. You take a tree with a bunch of branches that you don't actually need, and you only pay attention to the stuff you do need, right? That is what AlphaBeta is doing. So AlphaBeta pruning is going to be applied to the MiniMax algorithm. And the way we're going to do it is to introduce 2 new variables. Who can guess what those 2 new variables are going to be called? Right? Alpha. So alpha is the best alternative for max on this particular path through the tree. Okay? So alpha was that greater than or equal to 2 that we were looking at. Beta is the best alternative for min on this particular path through the tree. And so if you want to try and, this is very hard to visualize, especially when you start getting really deep cuts in AlphaBeta. But the way I look at it is that at some point in the algorithm, you're going to have, okay, my maximizing player knows that I have to be greater than or equal to this thing. My minimizing player knows that I have to be less than or equal to this thing. And so it's kind of a window. And if we see values outside of that window, we can just ignore them. And so we're narrowing and narrowing our search and becoming more and more efficient as we carry on with AlphaBeta search. Okay, so we recall before, this is the MiniMax algorithm when we split it into max value and min value. Now let's look at max value and min value if we introduce the alpha parameter and the beta parameter. So you can see here that this was max value and min value, and all we're doing is adding 2 lines of code and a couple of variables. So it's not that big of a difference, okay? So this is what we're doing. Let me tab back and forth to just show you how little of a difference it actually is. And what's happening here is that we're going to say, we're introducing alpha and beta as parameters to the function. And down here, we're going to do two extra checks that says if v prime is greater than or equal to beta, return v. This is for the maximizer. If v prime is greater than alpha, then alpha is equal to v prime. And so this line is the cut, saying that if we see something outside of our window, stop doing computation and just return the value. This line right here says if we see a new best value, then set that equal to alpha. Okay? And the opposite happens over here for the min value. Now, I'm going to give you a very well illustrated example that hopefully it really helped me understand the AlphaBeta algorithm, and hopefully it will help you understand the AlphaBeta algorithm. And a really important note for the AlphaBeta algorithm is that all of these values are passed by value, okay? Not passed by reference. So that matters for the implementation, is that the state, the alpha, the beta, and the depth, you are passing that by value, meaning you are passing copies of those variables. So those variables will propagate downwards in the tree, but they do not propagate upwards in the tree. And I'll show you what that means with this very well illustrated example. Okay, so here's a sample tree that's going to go to depth 4 that has a bunch of values down here. Those are my leaf nodes. That's the terminal nodes with those evaluations. And we're going to apply the MiniMax algorithm with AlphaBeta pruning to this tree. So we're going to apply max value to the starting state. Alpha initially gets minus infinity because it's trying to store maxes. Beta gets plus infinity because it's trying to store mins. And the depth at the top of the tree is 0. So that's how we call this. Now, so here is, what's going on here? Okay, here is what's going to happen. The min value and max value algorithms are going to be called. So at the top of the tree, blue is max value, min is min value. So I essentially keep going down until I get to a root node, right? Or until I get to a terminal node. Because this just says, okay, if it's not a terminal node, go down and switch from max to min. Then min will say, if it's not a terminal node, go down and switch from min to max. So I don't really do much until I get to an evaluation node. However, so let's just do this. Okay, so my value here, I have, if you see a negative here, it means negative infinity. So here, my v is negative infinity. That is my current best value. My alpha is negative infinity because that's what I passed it in as. Beta is positive infinity, which is right here. So v, negative infinity, alpha, negative infinity, beta, positive infinity. Now, down here, I'm going to be keep track. So I don't have an evaluation node, so I can't do anything yet. So max calls min, and so I go down in the tree. Min here is trying to store a negative. So as you see in the algorithm, this v for the min value is positive infinity. So that's why this is positive infinity here. Alpha and beta get passed down. Alpha is still negative infinity from this call of the function. Beta is still positive infinity. Well, we still don't have an evaluation node, so now min calls max. And now again, max calls min. But now I am at an evaluation node down here. Okay? So here, for your viewing pleasure, is the MinValue algorithm. It's going to look at these and do the following. So here's my v prime, 8. My v is currently positive infinity. My alpha is negative infinity. My beta is positive infinity. Here's what the algorithm says. If the new value is less than the old value, then set it as the old value. Okay? So that's what I'm doing. I'm going to set that. So now, I'm doing all three. If the new value is less than or equal to alpha, then just return the value immediately. Well, alpha is negative infinity, so this is not going to be less than negative infinity. So I'm not going to do this pruning step. The other step says if v prime is less than beta, then beta is equal to v prime. So that is true. So I'm going to set beta to v prime. So here what I've done is I've set v equal to v prime, which is 8, and beta equal to v prime, which is 8. Now we're going to look at the next one, right? So the next one is going to say, okay, is 7 less than v, which is 8? Yes, it is. So I'm going to set that. Is it less than or equal to alpha, which is minus infinity? No, it's not. So I'm not going to be returning the value. If v prime is less than beta, beta equals v prime. So after looking at that, I can say, okay, yes, I did set a new value because 7 was less than 8, which was v, and 7 was less than beta as well. So now I have finished this particular node's minimizing step. So now I look at this maximizing step, right? Because the maximizer is trying to minimize over these things. So this step says, now we're trying to maximize, so we're doing greater than. Look at this value. If that's our new v prime, if that's greater than v, then v equals v prime. So is it greater than minus infinity? Yes, it is. Okay. Is it greater than or equal to beta? Beta is positive infinity. No, it's not. Is it greater than or equal, or is it greater than an alpha? Well, alpha is currently negative infinity, so yes, it is, right? So that's what we set. This is the result of applying this with 7 to our current values. And now we look here. This is so we have this as our current step. We currently do not have a terminal node, so we call minimizing. But look, this is our first example of where our value of alpha now is no longer positive infinity, right? So alpha value gets passed down. So what this means is, through the part of the tree that we have looked at so far, this person up here, this node is a maximizing node, and it knows that its value is going to be greater than or equal to 7, right? So keep that in mind. That's what the alpha means. Alpha is the top end. Like, it's going to be at least that. Well, actually, it's the bottom end. It's going to be at least that much. So now we get to a terminal node, and we're looking at the min value. So it says, is this value, v prime, which is 3, is that less than v? Well, v was positive infinity, so yes. And so we're going to set this v equal to 3. Is v prime less than or equal to alpha? If so, just return v. So look at this. 3 is less than alpha, which is 7. So what this means is, essentially, at some point higher in the tree, namely right here, this node knows that the value it's going to get is going to be at least 7. But we're currently minimizing with a 3, so I know that the value that gets going to get propagated upward is going to be at most 3. So that's not going to be at most 7. So it doesn't matter what this value is. I can just stop my computation right here and return the value of 3. Now, this node finishes its maximizing. We know that this is not going to affect it. And so these are the values that we are left with when this is finished. And so the value of that node in the tree is 7. Now, if the value of this node is 7, the minimizer is looking at that value, and it's going to set its values. So is it less than or equal to positive infinity? Yes, it is. Is it less than negative infinity? No, it's not. Is it less than beta? Yes, it is. So we're going to set those values to 7. Now we go down through the tree again, we go down through the tree again, but we look now that we have a beta value that we are carrying down through the tree, right? So this beta value is going to be that minimum value. So it's the opposite of an alpha cut. It's a beta cut. So we look here and we say, okay, these are our current values. Is v prime less than v? Well, yes, it is. Is it less than or equal to alpha? Alpha's negative infinity here, so no, it's not. Is it less than or equal to beta? No, it's actually not. So this is the first time where we haven't found a new minimum. So when we finish this looking at this node, we have v equal 9, beta equals 7, alpha still negative infinity. Now we look at this one over here. I won't go through all those steps again, but essentially it's not a new beta, but it is a new value. So we set that value. And now we know the value of this node is an 8. Okay? So now we go through the maximizing step because we've seen this value. Is it a new v? Yes, it is, because it's greater than negative infinity. Is it greater than or equal to beta? Oh, look, it actually is, right? So what's this doing? Well, up here, this is really interesting. So it's the opposite of the last time we pruned a node. This node knows that this is going to be, because it's minimizing and it has a current value of 7, that in order for something to be better, it has to be it has to be less than 7. But this is a maximizing node that's going to be at least 8. So because if this is going to be at least 8, but this one wants less than 7, nothing we do down here is going to matter. So I can prune the computation of that entire part of the tree, return that 8, and then this node does its update step and finds that this is not a new best value. And so this node now gets the value of 7. Okay, hopefully you're following along. I know it's a little bit complicated at first, but just alpha is saying that things have got to be bigger than this, and beta is saying things have got to be smaller than this, right? All right, so up here, now I'm back at the root node, and the root node now has a value. So I can set my value of v, and I can set my value of alpha. Beta doesn't change. Now I go down, so I've got a v value, I've got an alpha value, I've got a beta value. Well, beta is still positive infinity. So I pass these down through the tree, right? Until I get to another evaluation. So let's have a look at what happens all the way down here now. So v prime is 1. Is v prime equal to, is v prime less than v? Yes, it is, because that's currently positive infinity. Is it less than equal to alpha? Oh, it is. So I can prune this one, because this one knows it has to be at least 7, but this one's going to be at most 1. So I can immediately return, I can stop computing this node and just say, okay, the value of this one is 1. I don't need to go higher than that, because this person is trying to maximize with a 7, so no matter what I do down here, it's not going to matter. Now, this one gets a value of 1. Its alpha value is still 7, so it's going to look down the tree. We keep going. This one says, okay, is it a new value of v? Yes, it is. Is it less than or equal to alpha? It is again. So I can do another alpha cut right here. This one is 6. Is 6 greater than 1? Yes, it is. Okay, so I've finished this computation with these two cuts. Now, this node up here has a 6. But watch this. This is where we start to get into the huge amount of savings with AlphaBeta. And I'm lucky to be able to fit this on one slide. This one up here, the root node, knows it's trying to maximize, and it already has a value of 7, right? So this one is trying to minimize, and it already has a value of 6. So this value is going to be less than or equal to 6 no matter what else is computed, right? Because it's minimizing over 6 and a bunch of other stuff. It's going to be at most 6. But this one wants it to be at least 7. So the alpha beta cut here says if this value is less than the alpha that I already have, then I can just return the value, because nothing over here is going to matter. And look at all that stuff that I didn't have to do. So this gets a value of 6. It is not a new best value. And so the value of the root node is 7. And you can see here that I didn't have to compute this. I didn't have to compute this. I didn't have to compute any of this or this. And I got the exact same answer as if I just ran the MiniMax algorithm. So what are the computational savings of this? Well, you can see how much it's saving, and it's a lot, right? You can picture this tree being like millions and millions of nodes or something and just not having to do that. It's incredible. So In a MiniMax search tree, the number of node searched is b to the power of d. And in AlphaBeta search, the number of nodes searched is approximately 2 times the square root of b. The square root of that. So if you previously could only search to depth 7, now you could actually search to like depth 14. And so a depth 7 program in a chess game is going to be a pretty bad program, but a depth 14 program may beat the world champion, right? So the cost savings are huge. Okay. Moving on. Let's recall. So these were the 2 algorithms, right? So this was my MaxValue algorithm with AlphaBeta. This was my MinValue algorithm with AlphaBeta. And just like I turned MinValue and MaxValue into MiniMax, I can turn them into one function with AlphaBeta as well. It's starting to get a little bit long here, okay? But there you go. So it's starting to get a little bit long, but that's all you can do. Sometimes algorithms are a little bit long. But essentially, all we did is took this thing, which we already understand, and then we wrapped it around this max, right? So if I'm maximizing, do the maximizing step. If I'm minimizing, do the minimizing step. So I don't need to explain that conversion because it's the exact same conversion as with MiniMax. However, we are algorithm nerds. Can we do any better? Yeah, we can. So let's look at how we can shorten the alpha-beta pruning step on MiniMax. So down here, well, this is just the algorithm. We've looked at this already. But what I can do is I can make it a little bit inefficient. So I can make it a little bit less efficient by taking this right here and moving it up. Okay? It has the same, we will get the exact same answer. However, in some cases, it's one extra step of computation. But I'm just rearranging this, and if you analyze it, it gives you the exact same result. Okay. Now what I'm going to do is I'm going to do the following. By reordering, what it allows me to do is now compare, instead of comparing V prime to beta, V prime is also going to be stored in alpha. It's not always going to have the exact same value as alpha, but alpha's value is always going to give us more information. So I can replace this V prime and say alpha. See, just look, right above it, I'm setting the value of alpha here. If it's a new maximum, set it here. And then I'm calling that V prime. So what I can do is just use alpha, right? And now what I can do is, where I was returning V, which is this value, well, that value is now stored in alpha, right? So here I'm storing V prime in V, but now I can just return alpha, which is also storing V prime. So because I'm now I'm comparing against alpha, and I'm also returning alpha, I can actually, all this V stuff is useless because I'm using alpha as that temporary max storage variable. So all this V did was help me compute the max. So I can get rid of V. And now I've deleted 2 lines of code, and now I can return V here. Okay? And what I can do instead, because I've gotten rid of this V variable, well, what I'm doing here is I have a temporary variable called V prime. The next step to shortening, I apologize if I'm going a little bit fast, but you can rewind this. The next step to shortening is I can recognize this. I'm using V prime as a temporary variable to store this min value, right? And then I'm just storing this here and then using it down here. But instead of storing a value and then comparing it, well, I could just compare its value directly by calling a min function, right? So instead of saying greater than, I could just use the max function. So now, instead of saying, okay, V prime is equal to this, if V prime is greater than alpha, alpha equals V prime. What I'm trying to say here is that alpha should be set to the maximum of the previous alpha or the new value. So I'm just going to say that. Alpha is equal to the max of the previous alpha or the new value. And then I can just delete these lines. Okay, so I have the exact same algorithm instead of, like, the exact same algorithm gives the same result, but fewer lines of code. Now watch this. This is really interesting as well. Here in this loop, if I ever have this cut, if alpha is greater than or equal to beta, return alpha. What is another way that I could return alpha here? Well, it turns out if instead of returning alpha, I just break out of this loop, well, the next line of code is also returning alpha. So if I replace this return alpha with just break, then it's the exact same thing, right? I can use break instead of return because we're returning outside of the loop. So I know this might seem like, what in the hell? Why would you do that? It turns out it's going to have a really, really good property in the next couple of slides. So we have break here, and now I have this sort of shortened version of the MaxValue algorithm. Now, what we're going to do is we apply the exact same logic, but we do it to the MinValue algorithm. Okay? I'm doing the exact same thing. So I didn't show it because I do literally the same thing, but to the MinValue algorithm. And where we were using alpha before, now we're using beta. That's it. And if you do that, you get this. Okay? But look, this over here says if beta is less than or equal to alpha, break. Well, what it used to say was return beta. Right? But before the break, I can just say break and return beta down here. But beta less than or equal to alpha, that's the same thing as saying alpha is greater than or equal to beta. So now what I have is, look at this. This line of code ends up being exactly the same. And if you ever have duplicate lines of code, then you can probably eliminate one of them. So let's keep going. Now we're going to take this and we're going to make these two min and max versions into the single long form version where we have an if statement. Okay? So what we're doing here now is we took both of these algorithms, min value and max value, we turned them into one algorithm. And so I just, like before, I put the maximizing part in here in the max, and I put the minimizing here in the max. But just look at this. Look at all these duplicate lines of code. I have a duplicate line of code here, and I have a duplicate line of code here. And really, the only difference that I'm doing here is the following. I'm maximizing over alpha. Here, I'm minimizing over beta. And here, I'm returning alpha, and here, I'm returning beta. So if I really want to be a super keener, what I can do is the following. Instead of putting all this code in the max, I can just put that if statement where I'm doing the different thing. So this becomes this. So this said for each child, I've put the maxes, the if max in here now. So if I'm maximizing, do the alpha equals max of whatever. If I'm not maximizing, then I'm minimizing. So this could just be an else, right? If I'm not maximizing, beta is the minimum of those things. If alpha is greater than or equal to beta, then break. So now you know why I wanted to put break in there. And if I'm breaking, well, when I return out, what do I want to return? Well, if I'm maximizing, I return alpha. Otherwise, I return beta. So this is the final shortened version of AlphaBeta. It returns the value of a state. And I'll get into that in a little bit. The result is exactly the same as the long version. Okay? So if you go back to that long version, which was like 30 lines of code, it will give you the exact same result of this. Implement whichever one you feel comfortable with. And however, I recommend starting with the long version. And there's a reason for that, which we're about to talk about. But the reason I showed you this entire derivation, okay, through all of these steps of shortening this, is because if you look online for the AlphaBeta algorithm, now you have it in the slides, so why would you look online? But I know that it's good sometimes to go out, look at other YouTube videos, get a second opinion, like get someone else explaining it. You are probably going to see something like this, okay? And if you saw this before getting this derivation, right? If you saw that version of the algorithm and I had taught you this version of the algorithm, which had different returns, different if statements, different almost everything, you'd be like, what the hell did Dave teach us? Why was it wrong? It's not wrong. It's just different, okay? It's just written different. So hopefully you appreciate that derivation, because I had been doing MiniMax for 10 years before someone actually, stepped me through this. But here's the last part that I have to talk about. In this algorithm, all we do is calculate the value, right? So all we know is how good that move is, or how good that state is. What we really care about is which action we should do, right? Which action should I actually do here? Well, what we have to do now is change this algorithm back to a long-form algorithm so that I can actually record the action that I want to do, right? So how do I do that? Well, the first thing I'm going to do is reintroduce that temporary variable v prime, because instead of just taking the max of something, I actually want to know when the max occurred so that I can set the best action. So that's what I'm doing here. I'm reintroducing this variable and I'm saying if max. So I went back a little bit in that derivation. So if max, I'm saying if max and v prime is greater than a, right? So now I'm back to saying if I'm maximizing and this is a better value. I'll show you why this is, but just bear with me. Now what I want to do is, how do I actually know where to record the value? Well, if we go back all the way to the tree, right? We have this tree and we're doing cool stuff in the tree. It's these actions that I care about, the actions of the root node. I don't care 10 moves from now which was the best action. I don't need to record all of those actions. All I care about is which action gave me the best value at the root node. How do I know in my recursive algorithm that I'm at the root node? Well, the depth was 0. So here, I'm going to put in one extra check that if I'm maximizing and I've found a new maximum, if the depth is equal to 0, then record the best action. So if I'm saying if I'm at the root node, record the best action. And so this, we can use some sort of global or state variable to record this best action, and I'll show you how to do that for our assignment. But here is the long version of AlphaBeta, and this is what I recommend doing for the assignment. It records your action for you, okay? And there's the recording of the action right in there in the long form version. Now, in the assignment, you're going to have a time limit. I know this is going to go just a couple minutes long. I'm sorry. What if we want to have a time limit in AlphaBeta? Well, we can't just say, okay, how many depth do I think I can search in a minute or a second? Because it's going to vary based on the game. So what we're going to do is we're going to look back in the course at iterative deepening. Remember iterative deepening I talked about? We're going to do iterative deepening AlphaBeta search. And this is what you're going to be implementing for your assignment. So for depth 1, 2, 3, up to infinity, we're going to perform an AlphaBeta search to depth D. When time runs out, we're going to record or return the best action from the last fully completed depth, because we can't trust an action from a search that didn't complete. What do I mean by that? Well, if we're up here at the root node, let's say I currently have a value of 7 for this action. And maybe I'm currently evaluating these nodes down here, right? If I have to stop the search while I'm evaluating these nodes, I have no idea what the value of this node could be. It could be 1,000,000. So if I have not finished that depth of search, then I don't want to trust it. So what I'm going to do is when the time runs out, I'm going to return the best action from the last fully completed depth. Okay? So how do you actually... Okay, now you might say, well, Jesus, Dave, I'm in the middle of a recursive function. How do I actually escape from a recursive function? How do I do that? Well, it turns out it's great in JavaScript. You can just throw an exception. So you're going to throw an exception. It will unravel all the recursion for you. It'll be great. So in assignment 3, here's what you're going to do. I have essentially written down a bunch of assignment 3 for you. You are going to have a number of variables here talking about the current max depth that you're searching, the best action, the current best action, the max player, etc. And you are going to have a function, which is eval. Okay, that's the heuristic function. You're going to have iterative deepening AlphaBeta. That's a function, and you're going to have the AlphaBeta function itself. Just like in previous assignments, this is your iterative deepening AlphaBeta function. I have written it for you on the slides in pseudocode. Actually, it's almost exactly JavaScript. It's depressing how much I've done of this assignment for you. Please don't go online and copy and paste someone else's AlphaBeta, because this is the iterative deepening AlphaBeta that I want you to do. And so what it says is, okay, here's how it works. Iterative deepening AlphaBeta is going to successively call AlphaBeta with gradually increasing depths. Hopefully we get to the end of the tree. Probably we won't. So I'm going to say, okay, I currently don't know what the best action is, so I'm going to set that to null. And the maximizing player is the player that's currently to move in the state. So if I have a game of chess and the black player is going to move, then the person who's maximizing is the person controlling the black pieces. Okay? Then I'm going to have my loop that goes for depth 1 up to some maximum depth, right? And then I go for every depth. So I'm going to say, I'm going to record a class variable called current max depth, set that equal to the current value of this iterator. Then I'm going to have a try catch statement. And what we're going to do is try to solve AlphaBeta up to that given depth. If AlphaBeta completes, then we will make it to this line of code, which will set the best action accordingly. All right? So we have two values here. We have the current best action. That is the best action that the current iteration of AlphaBeta is thinking is the best action. That's being recorded. Only if AlphaBeta completes its run will this line of code be called, and then I'm going to say, okay, that level of AlphaBeta was completed, therefore I trust it, therefore record the new best action. If it wasn't completed, it's because I threw an exception. Let's call it a timeout exception. You can call this exception whatever you want. If we timed out, then as you know, hopefully, if you catch an exception, the try block, it gets removed. Like I stop executing this try block. I go straight to the catch and I skip setting the next best action. So that's how we only trust the actions from completed AlphaBeta depths. So we catch that, we break out of this loop, and we're done, and we just return the best action. So that is iterative deepening AlphaBeta. And here, this is AlphaBeta. This is the entire algorithm that you have to write. You can take this and translate it into JavaScript, and your algorithm should just work. Okay? So it says, if the state is terminal, or the depth is greater than my current max depth, which was set by iterative deepening AlphaBeta, then I should return the evaluation. So that is a terminal node. It's a leaf node in my search tree. Otherwise, if my time elapsed is greater than the current config's time, throw a timeout exception. So that's how I stop my search, is I just throw a timeout exception. Otherwise, if I'm maximizing, do the maximizing step of AlphaBeta, or if I'm minimizing, do the minimizing step of AlphaBeta. What I recommend for assignment 1 is, because AlphaBeta can be a little bit tricky, maybe implement MiniMax first. Okay? So start out by implementing MiniMax. Once you get MiniMax to work, then just put in the extra variables for AlphaBeta and see if you can get that to work. Okay? Because remember, AlphaBeta is just an improvement to MiniMax. It is not a different algorithm. Here's the shortened version of AlphaBeta. So you can put this in there if you want to. However, just understand that this version is going to be a bit harder to debug than this version. Typically, it's a good rule to know that the shorter your code, the more things are happening per line, and so the harder it will be to debug, basically. And AlphaBeta is kind of difficult to debug. So some exam questions. Know the relationship between MiniMax and Nash equilibrium. Know the MiniMax and AlphaBeta algorithms. You may be required to regurgitate them. You need to know, why is iterative deepening necessary to implement something like a time limit? Why did we need iterative deepening for that? How AlphaBeta pruning helps MiniMax. What exactly is it doing? And given a tree with leaf values, compute the MiniMax or AlphaBeta values that were returned. So that tree that I showed you, right? Let me just go back. If I give you this tree with these values, you should be able to do MiniMax on that and give me the resulting value up here at the top. You should be able to do that.